Mr. Anshuman Sathpathy is a research scholar at Aquatic Chemistry Lab, Washington University, St. Louis, USA. He has pursued his MTech from IIT Kanpur and has been working on heavy metal geochemistry, which is basically focused on uranium. Today, today's session will provide a new idea to the participants about the other aspect of civil engineering, that is environmental science. I would like to thank him for taking pen and giving us the time from his busy schedule as it's 10:30 at USA in the night. So without taking much time, I would like to say, sir, you can start the session now. And Suman sir, please.
Shuman, your mic is unmute.
Yeah. Sorry, my mic was muted. Thank you, Shubham, for thank you, Nivedan, for inviting me. It's pleasure for me to be able to share my research with all of you, especially the undergrads. Um, so environmental engineering is one of the very important field of civil engineering, but it's seldom gets mentioned. So today I'm going to talk about uranium remediation. As you might be knowing, especially being located in a mining zone in Jamshedpur and not far from uranium mines, right? Uranium is actually a very important heavy metal, and uranium remediation is a challenge worldwide. Why are we concerned about uranium? Uranium is found in many different isotopic forms, as many of you might know. Among them, U-236 and U-235 are highly radioactive and they are carcinogenic. Uranium-238, which is not very radioactive, but it has got chemical toxicity, especially it's bad for kidneys. And out of all these isotopes, we get uranium-238 in much abundance in the subsurface. These are the main sources of uranium, as you can see. Mining and milling activity of these uranium ore. If you go to Jadugoda, it's not far from Jamshedpur, or if you could go to even Turamdi, which would be the nearest uranium mine from Jamshedpur, you can see a lot of mining activity happening and how it affects our environment. Apart from that, a lot of defense manufacturing, they use depleted uranium, which is mostly U-238. And then once this uranium, the radioactive isotopes of uranium, which is the nearest uranium mine from Jamshedpur, you can see a lot of mining activity happening and how it affects our environment. Apart from that, a lot of defense manufacturing, they use depleted uranium. I can hear my reflection, and then the echo, it's very strong. Once this uranium, the radioactive isotopes of uranium.
Okay,
Shubham?
now, yeah, now
it stopped. Thanks. Yeah. So yeah, thanks. Sorry for the technical glitch. So the main source of radioactivity as such is the spent nuclear fuel, which goes in the, which comes out of the nuclear power plant. So it is the waste material which comes out of nuclear power plant. And so here is the background for spent nuclear fuel. Almost 10% of global electricity production in 2017 was nuclear. And almost all of it was based on uranium. And if you can see this, this is the process which on the right side of the screen in which spent nuclear fuel gets generated in the nuclear power plant. So first you take the nuclear fuel, which is mostly U-235, and then nuclear fission takes place and you get the energy out of it. And then even after fission, a lot of radioactive uranium is still left in the waste material. This comprises of almost entirely, almost more than 90% uranium, and it's basically uranium oxide. This material is highly radioactive. It releases a lot of heat, and to bring down its radioactivity, it would take like 100,000 years, like almost 1 lakh years. And its long-term behavior is not fully understood. So we don't know how this material is going to dissolve in subsurface, how is it going to change its solubility. So which is very important for remediation of any waste material. So this is what we know about the uranium oxide. The oxidative dissolution of uranium oxide leads to production of uranyl ion or its complexes, aqueous complexes in water, which is uranium 6. So uranium oxide is uranium 4. It's +4 oxidation state. On oxidation, it forms +6, which is very highly mobile compared to uranium 4. And its solubility or its mobility is more than 1,000 times as compared to uranium 4. So once oxidized, uranium can be highly mobile. Now, how to remediate that uranium 6, so which is very highly mobile? We can absorb it onto a material which has very high specific surface area, which is a term we use for sorbent material or adsorbent. So, and specific surface area is basically surface area per unit mass of the material. But it has got a enemy, which is carbonate. Why? Because carbonate can bind to uranium 6 very strongly. And in groundwater in the subsurface, we have a lot of carbonate. It can bind very strongly to uranium 6, and it can dissolve uranium 6 from the binding material, and it becomes again highly mobile. So again, what could be another alternate? We adsorb it onto high specific surface area material. It's very less mobile. And again, if we can somehow reduce it into uranium 4, so once it's adsorbed onto this sorbent and it gets reduced to uranium 4, and if it comes in contact of carbonate, now uranium 4 carbonate species are very weak. So carbonate should not be able to dissolve uranium 4, and our problem gets solved. So what would be our ideal material? Our ideal material needs to have high adsorption capacity, and it should also be able to reduce uranium 6 to uranium. Now, I gave you all this background. Now, here is in this one slide, I'm going to summarize actual problem of using some high specific surface area material to remediate spent nuclear fuel, which is basically uranium oxide, which is generated as a waste. So, and that material is basically clay. So here we are going to talk about one particular clay, which is called Montmorillonite. Montmorillonite is known for low hydraulic conductivity, very high self-swelling capacity, so it can pack very well on its own. It has large specific surface area and high adsorption capacity. So what is being thought of as a long-term strategy for confinement of spent nuclear fuel, which is highly radioactive, is first, so as you can see in the graphics on the left side of the slide, most of these spent nuclear fuels will be packed into these primary containers, which are made up of copper or other metal. And then these containers will be lowered inside the deep underground repositories. These are almost like 300 to 500 meter below the ground level. So like deep mine sites are very ideal location for remediation of SNF. And then bentonite clay is a candidate material for packing of these containers. So now what is bentonite? Bentonite is almost more than 80% Montmorillonite. So then it's very important for the scientific community to know how Montmorillonite, how uranium and Montmorillonite behave with each other, how uranium gets adsorbed onto Montmorillonite, how it can desorb, and how its solubility can change. And guess what? We have a lot of studies done on uranium-6 and Montmorillonite. But one important aspect that people have not covered yet is that Montmorillonite is not reductive. So if uranium-6 is adsorbed onto Montmorillonite, it is still in the uranium-6 form or +6 oxidation state, and it can get dissolved by carbonate. So we thought of reducing this Montmorillonite into a processed form, which we are calling reduced Montmorillonite, and then use that as our sorbent. So what we used, this is a already widely used method for Montmorillonite reduction. And again, it has been done in the lab scale. It has not been demonstrated in field anywhere. And again, we do all our experiments inside the glove box, which is basically an anoxic chamber where you have no oxygen. It's a mostly nitrogen chamber, where we purge the Montmorillonite suspension with oxygen scrubbed gas mix, which is mostly nitrogen, overnight, and then add this buffer material, sodium bicarbonate and sodium citrate, and then heat it at 70 Celsius for 4 hours. And meanwhile, we add sodium dithionite, which is the reducing agent here. It's a chemical reductant. And after 4 hours, we see significant change in the color. And after that, we just rinse it 3 times with sodium chloride to get rid of extra citrate or bicarbonate ions. So you can see the change in the color on the right side of the screen, the graphic. So Montmorillonite is almost muddy looking. It's like clay, normal clay color as we are. And reduced Montmorillonite is almost milky. No, and it's because iron 3, ferric iron is found in the Montmorillonite structure, which is reduced to iron 2. So now the question is this structural iron 2, which is formed in the reduced Montmorillonite, can it reduce U6 to U4? If it can, our purpose is solved. So in there are some background studies which we referred. So iron 2, which has been found in the clay, there are some clays which have iron 2 in them. They have found to be reducing various organic pollutants. And there's one study done in 2010 where they adsorb iron 2 on the Montmorillonite structure. Instead of reducing the structural iron 3, they absorbed iron 2 on the unreacted Montmorillonite. And that adsorbed iron 2 could reduce uranium 6. So for our purpose, how do we plan our experiments? We took uranium 6 and we took clay solvent, especially reduced Montmorillonite, and then we combine the two, whether after reaction, the uranium 6 is still going to remain as U6, or is it going to reduce to U4? So if we can characterize the solid after reduction, we can figure out whether it is reduced or not. So these are the experimental conditions we chose for our purpose. We took uranium 6 loading of 50 micromolar for Montmorillonite mineral, the Montmorillonite clay, and then we also took did these studies for two different pH 3 and pH 6, which are again two extreme end of the pH condition we are expecting. And then the sodium loading, again, I haven't described the role of sodium in the clay mineralogy. So basically, sodium suppresses certain, so if you have high sodium loading in some clay suspension, it suppresses certain kind of sites, which we are basically called cation exchange sites, which are found in the interlayers of the clay. And so high sodium loading basically reduces or suppresses these cation exchange sites in the clay. And similarly for reduced Montmorillonite, we chose a lower uranium 6 loading, almost 10 times lower. And then again, the same pH and sodium condition. And we did all these experiments, under anoxic condition for 24 hours at 500 RPM. After 24 hours, we collected this solid and partially dried it and sealed it for the characterization purpose. So how do we know whether our solid has U6 or U4? So the very powerful tool for this purpose, which is our oxidation state analysis in the solids, is X-ray absorption spectroscopy. There are very few limited places where we have this facility of X-ray absorption spectroscopy in the whole world, and we actually wrote a proposal for getting to analyze these samples in Argonne National Lab located near Chicago. This is what we found. So these are the two different standards, I would say, One is uranium-6 adsorbed onto Montmorillonite. So Montmorillonite is not able to reduce uranium-6. It's not supposed to. So I'm assuming all the uranium is going to stay as uranium-6. And on the right-hand side, you can see uranium-4 is adsorbed onto reduced Montmorillonite. Again, I'm not expecting any U6 presence in these samples because reduced Montmorillonite has no oxidizing, it cannot oxidize U4 to U6. So these are the two standards. And again, in the bottom of the right side graphic, you can see the spectra generated for UO2. And one thing you should be able to notice the difference in the shoulder part of this left-hand side and the right-hand side. So U6 spectra is remarkably different from U4 spectra. So if our sample, our samples which are U6 adsorbed onto reduced Montmorillonite, if they have already reduced into U4, they should look more like the right-hand side and less like the left-hand side. So did we see that? Yes, we did. So we started with U6 and we adsorbed onto reduced Montmorillonite, and we found that after 24 hours, most of it is reduced, as you can see from the graph in the bottom. Now, we did something called linear combination fitting, where it's like you take two different spectra of two different standards and try to fit your spectrum of the sample. And so this is what we found with the linear combination fitting. At low sodium loading, there was almost all of it is, like almost 100% of uranium is getting reduced to U4. Whereas at high sodium loading and of course, near neutral pH was around 6.29, we found around 25% uranium did not get reduced. It stayed as U6, but at more than 75% is reduced to U4. Now, could carbonate dissolve this uranium? So as I was mentioning, if it is U6, it should be able to dissolve by carbonate. But if it is U4, carbonate does not form very strong complexity, so it should not dissolve uranium. So what we did, we added 10 millimolar sodium bicarbonate after the adsorption has taken place. And after 24 hours of reaction, we let it react for another 2 hours. And this is what we found. So after 2 hours, the extraction of uranium, only around 20% of uranium got extracted for the high sodium sample. Whereas both the low sodium samples, the extraction was very minimal. So this clearly correlates with our excess, where we see almost 25% uranium is actually in U6 form in the high sodium case. So this concludes this presentation. We could able to reduce uranium. We could able to reduce iron 3 in the Montmorillonite structure by dithionite method. The reduced Montmorillonite is able to reduce U6 in absence of oxygen. The U4 reduced Montmorillonite solids which are formed are chemically different from UO2 solid or uranium oxide. And carbonate is not able to dissolve uranium-4, which is bound to reduced Montmorillonite. And that actually shows we are able to successfully propose a method for remediation of uranium in subsurface environment. And currently, this work is this work I'm trying to compile it in a journal article, and it's very near to submission. So soon you will see this work published in some reputed journal. I would like to acknowledge, without whom this work could not have been a success, my advisor in WashU, Dr. Daniel Jamar, and Dr. Jeff Catalano, who is another professor in WashU, and he's also my thesis committee member, my colleague Kaushik Mitra, and my university and my university community. And last but not the least, National Science Foundation, which is the funding agency for my PhD work here. And thank you all for listening.
Yes, Shivam.
Okay, there are some questions.
I'm keeping the slides on so that.
The first one is other method like X-ray spectrometry to check the absorption.
Spectrometry?
To check the absorption of uranium. Okay.
So we use X-ray absorption spectroscopy. So basically, we are trying to find the oxidation state of uranium, and in a solid state. So there are a spectrometry method which we can measure the oxidation state in the dissolved state.
And the second one is like the clay mineral which absorbs the uranium. Should we put it in a concrete structure or it is directly buried into the ground?
In these repositories?
Yeah.
Yeah. So in the repositories are, I mean, we don't have anything planned in India yet, but most like countries who have been using uranium for a very long time, like you will find it in Russia, in Australia, most of the European countries, in the US as well. So what are the plan is, concrete is not a good packing material in those environments, because uranium, these SNF are they are going to release a lot of heat, and then the concrete will crack. And so good confinement is using a metal which is kind of more malleable, and then confining with clay, which is thermally stable. It's not very, it expands when it swells with water, but it does not develop crack if it is moisturized properly. So concrete, I won't say is a good material. Next question, please.
What is the interaction between sodium loading and uranium reduction?
Okay, so sodium, so I did not mention that thing here in detail, because keeping in mind it's the format of today's session. Sodium actually suppresses the cation exchange sites. So clay have this flaky structure, you know. So there are interlayers within the clay. So the interlayers have a lot of sites where the cation can directly exchange. So these are occupied by sodium. So if we have a lot of sodium loading, these sodiums, the uranium cation, uranyl cation cannot exchange with this sodium. So it actually suppresses a lot of those sites which can actually bind with uranium. So that's why when we have high sodium loading, a lot of uranium is not able to adsorb onto those cation exchange site. And my guess is that these cation exchange sites have a large fraction of uranium is getting reduced in those cation exchange sites. When we don't have high sodium loading, we see that almost entire uranium-6 is getting reduced. But in absence, when we have high sodium, uranium-6 is not able to get absorbed onto those cation exchange site, and then that residual portion of uranium-6 is not getting reduced.
And one more question is, how efficient is this process in terms of cost?
That I'm not able to answer yet. We have done it in lab scale, and definitely, I will say most of these countries are seriously thinking about using Montmorillonite, which is unreduced or unreacted Montmorillonite. And dithionite reduction is very commonly known method. So in the field, I mean, implementing in the field could be that we just pack everything in the clay, the Montmorillonite clay, and then we pump a slurry of dithionite inside so that the clay gets reduced in situ. I have no idea. I mean, I think soil engineers will be able to answer better this question. Next question, please.
Next question is, what is structural Fe2?
So in the clay structure itself, so clay is made of what? Aluminum oxide.
Yeah.
I'm sorry. So in the clay structure, it's mainly formed of aluminum and silicon, right? But iron is found as an impurity in clay. So some of these aluminiums are replaced with iron. And generally iron, we find ferric iron, that's what is available. Like if you leave anything in oxygen atmosphere, it will be iron 3 and it won't be iron 2. So this iron 3, which is found in the clay structure, is reduced to iron 2 during dithionite reduction. And that iron 2 is reducing your uranium-6 to uranium-4.
One more question is, which out of uranium-4 and uranium-6 is more soluble in clay minerals, and how does it affect the remediation more or less?
So we don't use the word solubility in clay minerals because clay minerals are solids. So we call it which is more able to adsorb onto clay minerals. So it's called sorption capacity. So clay minerals have certain sorption capacity, and I think both U6 and U4 both are quite strongly, they can strongly bind to clay. Clay can bind anything. So the problem is carbonate. So carbonate, if we have high carbonate loading in the subsurface, it can bind with uranium-6 and form aqueous U6 carbonate complex, and uranium-6 will be again mobile. But uranium-4, it cannot react, it cannot form strong complex with uranium-4. So uranium-4 does not get dissolved from the clay structure. So that's why we are proposing reduction into uranium-4 as a successful remediation technique.
Can other materials like heavy metals and other pollutants play the same role as uranium in clay minerals?
It depends on the chemistry. It depends on the charge on the species. So like uranium in low pH, it is cation. At high pH, it's anionic. So its chemistry will be different at low pH and at high pH. Chromium, on the other hand, based on its oxidation state, it can be either cationic or anionic. So like chromium 3 is cation, chromium 6 is anionic. Likewise, we have arsenic, we have all other heavy metals, which are of a lot of concern. And its chemistry with the sorption chemistry essentially depends on the pH and the charge, whether it's cationic or anionic, and what pH range we are talking about, and carbonate loading. So these are the factors, and oxidation state, of course, because that determines the charge behavior of the heavy metal.
And one more question is, which I think is out of the context of this session. Why uranium is used as nuclear weapon?
Why uranium is used in nuclear weapon? Is this the question?
Yeah.
I don't know. Maybe there's been hydrogen bomb as well, but I am not concerned about the weapon as such, because that's another thing to deal with. Because once the weapon is used, you cannot get the waste as in a small location, right? But nuclear power plants, they generate the waste in one point source. So nuclear power plants are point source of uranium waste. So, and we can deal with it if we know the science.
Okay, so that's all from question side.
Great.
Thank you, sir, for your session. This was really informative and will help the students to go to the other aspect of civil engineering, that is environmental science.
Yeah. I mean, I don't know whether UCIL allows any field trips or not, but you can take some of your students in some UCIL facility.
Okay.
Because a lot of this mining and milling is basically a lot of civil engineering as well.
Yeah. Okay, sir. Thank you for your session once again.
Yeah. Thank you.
Okay.